We can start. So this is the last talk of the session. My name is Pierre-Olivier Bouchard. I'm working at the Center for Material Forming Processes, and today I'm going to talk about modeling of liquid fracture at the microscale and for heterogeneous microstructures. So this is part of a French project called COMINSIDE with colleagues from Centre des Matériaux and LMK Cachan. So the idea of this project is to be able to observe, understand, and then model by a finite element approach liquid fracture mechanisms by means of in situ X-ray laminography on different materials, aluminum alloys and nodular cast iron. And today I'm going to talk only about nodular cast iron, but if you want to see some results about aluminum, there are two also very interesting talks in the conference. So the idea would be to be able to understand what's occurring in terms of damage mechanisms, so nucleation, growth, coalescence, and to try to reproduce these mechanisms. So, for example, here you have a tensile specimen with two ores here. These are the nodules here, and when you pull on the specimen, you see void growth. You start to see some coalescence occurring between voids. So this is a necking kind of coalescence, and then sometimes you even have shear localization and final fracture occurring at the end. So we would like to be able to reproduce these kind of mechanisms, and for this we need first to mesh the microstructure. This was done recently with a mesher which enables to mesh 3D heterogeneous microstructures. And so we are able to reproduce a RVE here, which is the exact microstructure of the one which is observed by laminography. Okay? But now if we want to reproduce the void growth and coalescence mechanisms, we lack one important thing, which are the boundary conditions. What kind of boundary conditions could be applied on this RVE? We cannot apply any kind of constant boundary conditions. Can we do a finite element microscopic simulation to extract the boundary conditions? This would be the aim of this talk today, to compare a finite element approach with another one coming from digital volume correlation, which gives us information in the volume about the displacement fields, and from which we can extract boundary conditions to apply on the RVE. Okay, so the outline of the talk will be a brief presentation of the FE framework. Then a few words about the nodular cast iron and the hypotheses which were made for the simulation. And finally, the application and the comparison of different ways of applying, of extracting boundary conditions on void growth coming from either FE simulations or DVC approaches. So first, the approach is based on level set functions to describe the interfaces between inclusions, voids, and the matrix, and on mesh adaptation. But first, we have to make some hypotheses. We assume here that the heterogeneities are only due to matrix inclusions and voids. We assume that the matrix is homogeneous and that we have an elastic one-Mises plasticity for the matrix, which at this scale is a big hypothesis. So we have these three level set functions whose zero values give you the interface between each phase here. And then we use a body-fitted mesh adaptation technique, which enables to automatically adapt the mesh to the level set functions, but also to mechanical fields. For example, here you have the kind of mesh we can get adapted both on the geometry of the interfaces of inclusions and the matrix, and also on mechanical fields, for example, plastic localization here. So we have a refined mesh also in these areas. And we can, by using remeshing, follow the evolution of voids and also adapt the mesh throughout all the simulation. This is an example of what we get. We have modules here, we have nucleation occurring. This is equivalent stress, and you can see the stress concentration, and also sometimes even coalescence, which occurs here. And so this works in 2D and also in 3D, but it's much more time-consuming. Okay, so this was just for the introduction about the FE technique. I can come back during the question if you want some more details. And now we can switch to the nodular cast iron. So we are going to perform two kinds of simulations because we are going to work on two different scales. If we work with the micro scale, then we have to assume that this is a B material for which we have a behavior for the matrix here, with elastic plastic behavior coming from this paper. And also we have graphite nodules, which have very low mechanical properties, and usually in the literature we used to assume that these nodules can be considered as ores in the FE simulation. So this is the hypothesis that we will consider in this work. Then if you model this material at the macroscopic scale, then you have to use an homogeneous material here, And we have also an elastic plastic behavior, and this time the behavior was identified by using low displacement observations and the IC measurements. So we have an elastic plastic behavior for the macroscopic behavior as well. Regarding the tests, so this is a tensile test with two holes drilled in the specimen, oriented at 45 degrees with respect to the loading direction. We have 0.5 millimeter diameter for these holes and 1.5 millimeter in between the centers. And for different scans during a tensile test, we will extract information in a region of interest, which is in between these two drilled holes here. And we will take into account all the nodules in this region of interest. So the laminography gives us the reconstructed gray level volumes at the initial scan, but also the 12 scans during the tensile test. So we will be able to follow the evolution of these nodules, of these voids, up to final fracture. We need to extract boundary conditions for the FE simulations. So for this, we're going to use a digital volume correlation approach in a domain which is larger than the FE domain, because during the tensile test, this FE domain will grow, and at each step, we need to have boundary conditions. And this is the reason why we have a bigger volume here. And we get displacement fields and these gray level residuals as well. And we will use these displacement fields as boundary conditions on the surfaces of this RVE. So this RVE here is meshed on the region of interest with P1 plus P1, so velocity pressure formulation for the tetrahedral elements. And we have also remeshing to follow void growth during the simulation. Okay, so now let's come to the application. The idea is to compare different ways of applying the boundary conditions. And for this, we will compare three different techniques. The first one, that we call weak FE, is based on two simulations. The first one is a macroscopic simulation at the specimen scale. We're going to mesh this material here to perform the simulation and to extract the boundary condition on the region of interest. And we're going to use these boundary conditions to apply at the micro scale on the RVE to perform a second simulation. Second technique is called the strong FE simulation. Here we have one single simulation at the macroscopic scale here, but we have a huge mesh refinement here in order to capture all the nodules, all the graphite nodules in the region of interest. If we zoom here, we have the mesh containing all these nodules, around 100 nodules in the region of interest. So we're performing one single simulation here. And finally, the last one is called the DVC FE simulation. We have one single simulation of the region of interest, and the boundary conditions are coming directly from the DVC approach. So for example, for this application, if we look at what is occurring at this scale here, you will see that this is plastic strain. You have linear displacement at the beginning, and then you will have an acceleration of displacement at the end, which corresponds to the last stages of coalescence. You can also see some coalescence occurring between some of the voids here. Here as well. Okay, so how can we compare FE simulations with experiments? There are different ways. The first one is to superimpose the interface between the voids and the matrix between simulations. The white curves are from the simulations with pictures from laminography. So these are 4 different stages here, and you can see that in some places the void growth and coalescence is very well described. If you look at these two voids here, you have void growth, which is well described, and also void coalescence, and even at the last stage, you have a very good representation of the pictures. At other places, it's not that good. If you look here, for example, the finite element simulation didn't capture the coalescence stage here, so maybe the plasticity that we're using right now is not the good one. Another way is to compare, in terms of high level residuals, the differences between the predicted FE simulations and the results from the pictures, the laminography pictures. We superimpose these gray levels, we make the difference between the gray levels of the laminography pictures and the FE simulations, and the black area here corresponds to the maximum of error that we get on the region of interest between the simulation and the experiment. If you compare the DVC FE and the strong FE simulation, you see that you have higher errors here, and we can assume that maybe this approach is less good than this one. But this is just a qualitative result, so we need quantitative comparisons. And for this, we're going to plot void growth evolutions versus displacement here. For the different techniques, black one is the experimental volume of the nodules taken from the laminography pictures. The yellow is the weak FE simulations. If you remember, the weak FE is the one for which we performed the first simulation in the macro scale, and then we extracted the boundary conditions for the micro scale simulation. But when we did this first simulation in the macro scale, what we assumed was plastic incompressibility. Okay, so when we apply the boundary conditions at the micro scale, what we observed is no void growth at all. Regarding strong FE simulation, we do have a void growth here because these voids are meshed directly in the single simulation, but we underestimate void growth, and it is linear, which means that we don't capture the void coalescence at the end. And finally, the DVC FE gives a good acceleration of void growth at the end. We have seen some coalescence filtering, which was interesting here, but we overestimate slightly the void growth compared to the experiment. So we're still trying to understand why we're overestimating this void growth. Two main reasons. The first one may be the graphite nodules that we assumed to be voids. Maybe they don't have very high mechanical properties, but maybe they will restrain void growth during simulation. And the other one is the plastic behavior that we took from a paper, and maybe this kind of approach should be used to identify elastic plastic behavior or even damage in the matrix at the microscope. Okay, so, still good?
That's a good show,
So conclusion. We have developed a new FE framework in order to be able to mesh the real microstructure and to be able to represent the nucleation growth and coalescence mechanisms for large plastic strain and different kind of loading path. Today the application was on nodular cast iron, and we've seen that an important thing is to find a good way of applying the exact boundary conditions, which is not as easy as it seems to be. And we still have a lot of ongoing work. For example, in the matrix, do we need to assume a second void population and to have damage to induce more softening and accelerate coalescence, for example? We have applications on other materials, and we hope that at the end, this kind of approach will enable to help us calibrate nucleation criteria for void nucleation. Here, numerically, it's possible to have both interface debonding and particles failure based on very simple stress-based criteria, but we don't know what are the thresholds that we should use for different kinds of materials. So we hope that at the end, this kind of approach will help us to identify this kind of thresholds. And this is the end. Thank you for your attention.